In this lesson, we're going to look at the substitution method to find the solution, or what we would call the intersection point if we were graphing, of a system of linear equations. Remember, a system of linear equations is two or more equations. For every equation, you will have that many variables. So if we have two equations, we have two variables. And that's what we'll be working with. There are three possible outcomes for the solution for a system of linear equations. One is that the lines will intersect, giving us one solution. Two is that the lines will be parallel, and we can tell that by looking at the slopes of the lines in slope-intercept form, and we won't have any solutions because the lines will not intersect. And three is we could have infinite number of solutions, which means the first line is overlaid by the second line because they're exactly the same equation when you go to graph them. Now, when we're solving by substitution, we still will be able to see if we have one solution, no solutions, or infinitely many solutions. But it won't be visually by graphing. So, the first thing we're going to do is by substitution, both equations have to be in slope-intercept form, which means y equal. So you really want them to be in y equals mx plus b form. If they're not, you would solve for y and get them there. We're going to be working with equations that are already in y equals mx plus b form or slope-intercept form. What you're going to do is you're going to set both equations equal to each other because they're both equal to y, so both the mx plus b's are equal to each other. I will demonstrate that in a minute. Second, we're going to solve for x. Then we're going to take the value for x and we're going to substitute it back into either of the two equations and solve for y. And then we can write that solution as a point. Okay, then we can plug in x and y into both equations and see that it actually comes out correct and check it. So that's going to be our methodology today. All right, so I'm going to keep those rules near us as we work on a problem. So our first problem in our notes is y equals x plus 2 and y equals 3x minus 6. So here is our system of equations. They're both y equals, which means they're in slope-intercept form. So since they're already in slope-intercept form, we are literally going to take the first mx plus b, and we're literally plugging it into y in the second equation by substituting. So really, ideally, what it means is you're taking each of the mx plus b forms and setting them equal to each other. And that's what we mean by set the equations equal to each other. They're both y equals, so both of what y equals equal each other. Next step is we're going to solve for x. So I'm going to bring this x to the right-hand side since the 3x is larger and I don't have to deal with a minus sign there or a negative sign. So if I subtract x on each side, that's a 0. I'm going to get 2 equals 3x minus 1x is 2x, and I still have minus 6. I'm going to bring the 6 over to the left side. 2 plus 6 is 8. These cancel out, and that still leaves me with 2x. And then I'm going to divide by 2 on each side to solve for x. And so x equals 4. All right, once I know what the value is for the x, then I can go back and I can choose either of the two equations to substitute in and get y. Okay. So we've done this step 2. Now we're going to substitute x into either equation and solve for y. Okay, and actually I'm going to leave that over there this way. Okay. So our x was equal to 4. So let's take the first equation, y equals x plus 2. And let's substitute in that x value of 4. And remember, you should always put parentheses around it in case there's a negative sign there or any other operation has to occur. And 4 plus 2 is equal to 6. So our solution is 1 point, which means these lines would intersect if we graphed them, but we're not graphing. And we would write it up as 4, 6. That's our answer. Okay, so we've done step 3, and we've done step 4. Now to check, the best thing to do is take each equation. So we'll start with y equals x plus 2. So this is our check. And we're going to plug in the 6 for y, the 4 for x, and we're just going to make sure that this equals the same, and it does. Now take the other equation, which was y equals 3x minus 6, and substitute in your 6 for y. Keep your 3, open up parentheses, and put in your 4 for x, and keep your minus 6. 3 times 4 is 12, minus 6 is 6, so 6 equals 6, and it's a check. And all that means is that you walk away knowing that the solution of 4, 6 that you got is correct. All right, so that is an example where we have two linear equations that if we were to graph them, we would see the intersection point, and it is 4, 6. All right, so now we have another equation. All right, this is y equals negative 2/3 x plus 1, and y equals negative 2/3 x minus 4. They're both in slope-intercept form, so we're going to set them equal to each other. So negative 2/3 x plus 1 equals negative 2/3 x minus 4. Now, there's no need to get rid of the fraction in here like we did in writing standard equations. I know you don't love the fractions, but keep them. Let's start solving for x. So let's bring this minus or negative 2/3 x over to the other side, to the left, by adding it, because if it's a negative, we do the opposite and we add it. And remember to take the x with it. So we do that on both sides, and what we wind up with is negative 2/3 x plus 2/3 x is 0. So we have no x value. So all we can bring down on this side is the 1. Equals. Now on the right-hand side, we have negative 2/3 x plus 2/3 x. Well, that's 0 again. And all we have left on this side is negative 4. So what's happened here is we've lost our variable. Okay? That doesn't always occur because some people like to move the numbers first, and then we're going to get our equations will be a little imbalanced. So really what happens here is you want to ask yourself, you know, if you move the numbers first, you're eventually going to move the x's, and you're going to get this equation that has no variables in it. If this happens and we've lost the variable, and that's what I usually say is we've lost our variable, two things can happen. So the question is this true? And that's what you have to ask. Is this a true statement? Is 1 equal to negative 4? And the answer is no in this case. 1 is not equal to negative 4. So if the answer is no, there is no solution. But if the answer was yes, there would be infinite solutions. So those are the two outcomes that can occur. So in our case, for this problem, when we have 1 equal to negative 4, and that's our final result, and we have no variable to solve for, the question is this true? Question mark. The answer is no, so no solution, and that's our final answer. And what that means, if we go back to our visual, if we have no solution, that means our lines were parallel. The way that we know our lines are parallel is they have the same slope. So let's look at our original two equations. Our slope was negative 2/3 on the first equation, and our slope was negative 2/3 on our second equation. So right away we know that we're not going to have a solution because these would be parallel lines. And parallel lines, as you know, never intersect. So you would not have an intersection point. So if you don't see this and recognize it right away, then you would go through the motions of solving an equation and get to this point. And then you're going to ask yourself, hey, is this true? And if it's no, there's no solution. All right, let's take a look at this equation system. All right, the first equation is in slope-intercept form, but the second one is not. So we're going to do a little bit of work on it to get it into form. We're good at this already. So we divide by 2 on each term. So we get y equals 4 divided by 2 is 2x. 2 divided by 2 is 1. And what do you notice? Okay. They are the same equations. All right, so here's our first equation. Here's our second equation, and they are identical. So they are the same equation. And if we remember from our visual, if we have the same equation that overlies the other when you graph it, then you're going to have infinite solutions. So a lot of us will actually be intuitive enough to memorize that. If not, and that's okay, we kind of get into like this mind warp and we just start doing what we got to do. Let's start taking the two y equals and set them equal to each other. So we take the first equation and we take the second and we set it equal. And we start to solve because, you know, that's what we do. So let's take the 2x to each side. 2x minus 2x, 0, gone. There is no x, don't write one. All we have left is a 1 equals. At 2x minus 2x is 0, that's gone. There's no x, don't write one. And that equals to a positive 1. And we get here. Again, we have lost the variable. We could have moved the 1's over and had 2x equals 2x. And we don't lose the variable, but we still have something that equals itself. We could work this all the way out and subtract from each side for all the numbers and the variables and get 0 equals 0. The bottom line is when you get here, you have to say to yourself, hey, if I have a number equals a number, and this is my final act, is this true? Is 1 equal to 1? If the answer is yes, then you have infinite solutions, which means it's the same line graphed over the same line. So it's going to depend on you and how you memorize and study for this. If you wind up with the same equations, you already know infinite solutions, no work to be done. If you forget and you just go through the motions of solving, when you get here, you have to ask, is this true? And if it's yes, it's infinite solutions. And that is how you solve systems of equations by substitution. And you have one of three solutions. Intersecting lines, we'll get one solution. Lines that are parallel, meaning we lose the variable or we have number equals a different number. It's not true that a number equals a different number, so they're parallel, no solution. Or we have a number equals the same number, which means it's the same line lying on top of another line graphed, which means infinite solutions.